You pull into a gas station, swipe your card, grab the nozzle, squeeze the handle, and, well, 2 minutes later you're back on the road. You've done it hundreds of times, maybe even thousands. And not once did you really think about what was happening underground, inside that nozzle or under that concrete pad. Because here's the thing, a gas station looks like nothing. A canopy, a few pumps, maybe a sad hot dog rotating in a glass case. But underneath all of that mundane surface is more than a century of relentless engineering. Problems that killed people, explosions that leveled city blocks, invisible vapors that turned ordinary refueling into a game of Russian roulette. Every single piece of the modern gas station, from the fiberglass tanks buried 8 feet below your feet to the tiny air hole at the tip of the nozzle, exists because something went wrong, someone got hurt, and engineers had to fix it. This is not a story about convenience. It's a story about how humans took one of the most dangerous substances ever commercialized and made it so boring that you don't even think about it anymore. If this is the kind of deep dive that gets your brain firing, do yourself a favor and subscribe right now. We go this deep every single week, and you really don't want to be the person who finds us 2 years late. Before gas stations existed, people were basically winging it. To understand why the modern gas station is a feat of engineering, you have to start at the beginning, when there were no gas stations at all. In the late 1800s, the fuel people used wasn't gasoline, it was kerosene, used to power lamps and stoves. If you needed it, you walked into a hardware store, an employee scooped it out of a barrel into a metal can, and you carried it home. That was the entire system. No pumps, no meters, no accountability whatsoever. When automobiles started appearing, people adapted the same method. You'd buy kerosene in a can, carry it to your car, and pour it through a funnel. And, well, you'd do it slowly, messily. There was really no reliable way of knowing just how much fuel actually made it in. They hadn't experienced the disaster yet, so honestly they didn't know to be afraid. Sylvanus Bowser built the first pump and changed the whole equation. In 1885, an American inventor named Sylvanus Bowser designed a hand-driven pump, a lever mechanism that forced kerosene out of a sealed container through a one-way valve and out through a nozzle. One full crank delivered exactly 1 gallon. That was a genuine revolution. For the very first time, fuel delivery was measured and controlled. These pumps started appearing on city streets, operated by attendants, but customers still had no way to verify they were getting what they paid for. They were trusting a man with a hand crank, and trust only stretches so far when money is on the line. The answer was the visible pump. Engineers designed a pump with a glass cylinder mounted on top. The attendant cranked fuel up into the glass tank. You could watch it fill to the exact line, and then gravity drained all of it down into your car. Transparent, accountable, and genuinely clever for its time, you could see exactly what you were paying for. The first real gas station opened in 1913, and honestly, the world caught on fast. By the early 1900s, the car market was accelerating at a pace nobody had predicted. In 1900, the United States had roughly 8,000 registered cars. By 1912, that number had exploded to 1.2 million. The curbside pump just couldn't keep up. Traffic backed up around every pump in the city. The small 50-gallon storage tanks ran dry constantly. And having fuel stored at street level was becoming a serious safety crisis. Gulf Oil Company solved this in 1913 by opening the first purpose-built filling station in Pittsburgh, Pennsylvania. They buried a large storage tank underground and connected it to 6 separate pumps, so, multiple cars could fuel up at the same time. On the first day, the station sold 30 gallons. By the end of that first week, it was moving 350 gallons a day at around 27 cents per gallon. The model worked. Word spread. And within years, dedicated filling stations were opening across the country at a pace that seems staggering, even by today's standards. When cars switched to gasoline, everything nearly went up in flames. Through the 1910s and into the 1920s, most cars made the transition from kerosene to gasoline. Gasoline burns more easily and delivers more energy per gallon, which made it the obvious choice as engine technology improved. But This switch introduced a problem that engineers didn't fully appreciate at first, and people paid for that gap in understanding. Kerosene has a flash point of 38 degrees Celsius. It only starts producing flammable vapor when it gets that warm. In most normal conditions, kerosene just sits there, stable and manageable. Now, gasoline, on the other hand, has a flash point of negative 40 degrees Celsius. That means it's producing flammable vapor at every temperature a human being could survive in. All day, every day, that vapor rises off the surface of the fuel. In early gas station designs, that vapor had nowhere to go. It built up inside the tanks and it drifted through the air around the pumps. All it needed was a single spark, static electricity, a cigarette, a loose wire, and the result was, well, catastrophic. This was not a theoretical risk. Fires and explosions at gas stations were a recurring reality in the early decades, and they forced engineers to fundamentally rethink how fuel stations were built and operated. Self-service was banned, and the reason tells you everything about the danger. Up until 1947, every gas station in America was operated by an attendant. You pulled in, they came out, they handled the fuel. This wasn't just a service model, it was a safety requirement. Trained staff meant controlled fuel handling. Customers were kept away from the dangerous parts. Then Frank Urich opened a self-service station in Los Angeles. His logic was simple. Remove the labor cost, drop the price. He cut his per-gallon price from 23 cents down to 18 cents and immediately drew lines around the block. Competitors couldn't match him. Regulators couldn't ignore him. Most states moved quickly to ban self-service stations. The concern wasn't just vapor and fire, it was overflow. Customers had no reliable way to know when their tank was full, and gasoline spilling across hot concrete surrounded by running engines is exactly as dangerous as it sounds. The engineering answer was the automatic shut-off valve. A float mechanism inside the nozzle rises with the fuel level in the car's tank, and when the tank is full, it mechanically closes the valve and stops the flow. Simple in concept, elegant in execution, and, well, the piece of technology that eventually made self-service legal across most of the country. What is actually buried under the concrete at every gas station you've ever used? This is where modern gas station engineering gets genuinely impressive. The average station sits above a system that almost nobody ever thinks about. The storage tanks are enormous, typically holding between 10,000 and 30,000 gallons each, buried anywhere from 4 to 8 feet underground. For most of the 20th century, these tanks were steel, and steel corrodes. Tanks would slowly rust through, leaking fuel into the surrounding soil and contaminating groundwater. The cleanup from that era is still ongoing across thousands of sites in the United States alone. Today's tanks are fiberglass. They don't corrode, don't react with fuel, and can hold up for decades without degrading. But the material is just the start. Every few days, a tanker truck pulls up to refill the station. As fuel flows from the truck down into the underground tank, the vapor that was sitting in the headspace above the fuel needs somewhere to go. In older systems, it vented straight into the atmosphere. But in modern systems, a vapor recovery line runs from the top of the tank back up to the tanker truck. The vapor gets pushed back into the truck, returned to the refinery, cooled, and converted back into usable fuel. So nothing escapes into the air, nothing gets wasted. As the tank approaches 95% capacity, a flapper valve inside physically closes off the fill point. It is mechanically impossible to overfill the tank. The system shuts itself down. The submersible pump buried in the fuel itself is doing more work than you realize. When you press the handle at the nozzle, the process that starts underground is not passive gravity. At the bottom of the storage tank sits a submersible electric pump, submerged directly in the fuel. This design eliminates air gaps in the fuel line and prevents vapor pockets from forming in the pipes, which could interrupt flow or create ignition risks. That pump pushes fuel up through a series of pipes and filters, through a calibrated flow meter inside the dispenser and out to the nozzle. The flow meters in modern dispensers are mandated by law and verified by government inspectors on a regular schedule. When the pump reads 10 gallons, it has delivered 10 gallons. The nozzle in your hand is, honestly, one of the most underappreciated mechanical devices ever made. The pump nozzle looks like a simple metal tube with a lever. It is not. It is actually a self-regulating mechanical system that uses fluid dynamics to shut itself off, and it does this without any electronics whatsoever. Here's how it works. As fuel flows through the nozzle, it passes through a narrow constriction. This constriction creates a low-pressure zone, a well-documented phenomenon called the Venturi effect. Small holes around that constriction connect to a thin tube that runs down to the very tip of the nozzle, the part that sits inside your car's fuel inlet. Because of the low pressure created by flowing fuel, air gets pulled in through that tube continuously while you're fueling. That same tube also connects to a sealed chamber containing a rubber diaphragm. The lever you squeeze is held open mechanically by a set of small ball bearings pressing against that diaphragm. When your tank is full, fuel covers the small hole at the tip of the nozzle. The air supply gets cut off. The low-pressure zone inside the nozzle now has only one source of air available, through the tube connected to the sealed diaphragm chamber. Because that chamber is sealed, the negative pressure, it sucks inward, pulling the diaphragm up. That movement releases the ball bearings. The lever system collapses, the valve closes, and just like that, fuel stops flowing. No sensors, no electronics, no software, pure mechanical physics, engineered to respond to one specific condition or a full tank, and shut itself down every single time. A century of getting it right produced something most people take entirely for granted. What started as a man with a barrel and a hand crank in a hardware store became a global infrastructure that pumps roughly 3 billion gallons of fuel every single day. The engineering that made that possible isn't flashy. You don't see it. You don't hear it. That's exactly the point. Every piece of this system, the fiberglass tanks, the vapor recovery lines, the flapper valves, the submersible pumps, the automatic shut-off nozzle, exists because engineers inherited a problem they didn't create and built their way out of it. Decades of trial, failure, fire, legislation, redesign, and refinement produced something so reliable that the only thing you notice is how quickly you can get back on the road. That is what great engineering looks like. Not rockets, not skyscrapers. Sometimes it's the thing you use twice a week without a second thought. If you made it this far, you already know this channel is worth your time. So subscribe, share this with someone who thinks gas stations are boring, and we'll see you in the next one.